welcome to the deep dive. Today, we're going to get into the work of physicist Victor Weisskopf.
Right.
He was this major figure in the 20th century who gave us a way to, understand how order just dissolves.
And how it dissolves into chaos in a way that's actually predictable.
Exactly. And that's why our mission today is to really get why we're calling him the poet of leak.
It's a great phrase.
It is, right? It's all about this one process. You have some kind of structured, coherent motion, like, say, an excited atom.
And that little bit of order couples to this huge, messy continuum around it.
The electromagnetic fields, for instance. And it trades that beautiful structure for just, well, heat. But it leaves a fingerprint.
That's the whole game. I mean, Weisskopf's work explains so much. It's why things decay exponentially.
That perfect, steady curve.
Why spectral lines have width, why they're fuzzy, and even how the vacuum itself retunes matter.
So to track all of this, we're using a concept from the source material.
The coherence ledger. It's basically the bookkeeping for all this. It says that for every bit of coherence or structure that you lose,
You pay for it.
you pay for it. A proportional amount of thermal energy or entropy has to appear. It's a perfect transaction.
A balanced book.
Yeah.
That idea is the thread we're going to follow today, all the way from atoms to nuclei. So let's start with maybe his most famous result.
The rule of decay.
We're going back to 1930, to the Weisskopf Wigner derivation. This was, the first really solid explanation for why excited states decay exponentially.
Right, that perfect curve, P of t, is proportional to e to the minus gamma t.
Which is strange when you think about it. It implies the system has no memory.
None at all. A purely quantum system with just a few levels would, oscillate. You'd get revivals, interference, all this complicated stuff.
A messy curve, not that clean, memoryless decay.
So the question is why? Why does it forget so perfectly?
And the answer is the environment it's talking to.
Exactly. The mechanism is that your one discrete excited state is weakly coupled to, well, an enormous number of other states in the surrounding field.
A continuum.
A continuum. And crucially, that continuum has to have a smooth, basically constant density of states.
Our sources use a great analogy for this.
The water tower.
Yeah, the excited state is like a water tower, full.
That's true.
If you just have one big pipe to drain it, the flow could be complicated, it could gurgle.
But if the walls are just riddled with thousands of tiny, evenly spaced holes,
The smooth density of states.
then the water level drops in that perfect, steady, exponential way. It's the sheer number of exit routes that makes the decay so reliable.
So that leak rate gamma, that's the number that tells us everything.
It's the key. It gives you the lifetime, tau, which is just 1 over gamma. And as we'll get into, it also gives you the width of the spectral line.
And this isn't just theory. We can, prove this in the lab.
Oh, absolutely. The Purcell effect is this in action. You take a quantum dot, which is like an artificial atom, and you put it inside a tunable cavity.
So you're engineering the environment. You're changing the density of states.
You are literally changing the number of leaky holes.
Yeah.
And you watch the decay rate, gamma, change in real time, directly proportional to what you did. You control the leak.
Okay, so that perfectly sets up the next idea. We're moving from how long something lives to, well, what it is.
From the time domain to the frequency domain.
If a system only has a finite life, it can't have a perfectly sharp identity.
Its identity has a deadline, and that identity is its spectrum. A spectral line can't be infinitely thin if the state that produces it doesn't last forever.
The source puts it so well. Identity equals spectrum.
And that spectrum has, like, a budget for its width. There's a fundamental cost, the natural width.
Which comes from the uncertainty principle.
Right. Delta E times tau is about h bar over 2. That's the price you pay just for existing in a vacuum that lets you decay. It's unavoidable.
But then there are other things that make the line even fuzzier.
Extrinsic factors. You have Doppler broadening from the atom moving around. And then there's collisional broadening.
And this is another place Weisskopf did foundational work.
Absolutely. He modeled collisions as these short, sharp kicks. Each kick just completely disrupts the phase of the atom's oscillation.
It resets the clock.
It resets the clock. So the more kicks you have, the shorter the effective coherence time and the broader the line gets.
So there's a clear trade-off here. It's a cost-benefit thing.
Always.
If you want a perfectly sharp identity, a razor-thin line, you have to isolate the system completely.
Which means it has to live forever. But if you want speed, if you want it to decay quickly, you have to couple it strongly.
And you pay for that in width.
You pay width for speed.
And you can actually watch this happen.
Yes, in a vapor cell. It's a classic experiment. You increase the pressure, which means you increase the collision rate, and sure enough, the line gets broader.
Just like the theory says.
But then, if you keep cranking up the pressure, something amazing happens.
Dicke narrowing.
Dicke narrowing. The line starts to get narrower again.
Why on earth would that happen?
Because the collisions become so frequent that the atom barely moves between them, the phase interruptions start to average out. The collisions actually become phase coherent.
So the chaos starts to create its own kind of order.
For a moment, yes. It's like synchronization is winning a brief fight against the leak rate. You're watching the coherence ledger balance in real time.
Okay, so if we can see that battle in a simple gas, let's scale it up. Way up.
To the inside of a nucleus.
Right, we're moving from atomic physics to the chaos of a nuclear collision. And this is where Weisskopf introduces this incredible idea of strategic forgetting.
We're talking about the compound nucleus model. And it was, deeply counterintuitive at the time.
The idea that you can predict what a system does by assuming it forgets how it started.
Exactly. A projectile, say a neutron, hits a heavy nucleus. The energy doesn't just knock another particle out right away.
What happens to it?
It gets scrambled, completely thermalized among all the protons and neutrons. The ordered motion of the projectile turns into, basically, heat. The nucleus becomes a hot, chaotic soup.
And the key insight is that by the time something boils off,
it has no memory of how it got there. The exit channel has completely forgotten the entrance channel.
So make the nucleus busy enough, and it forgets your name before it says goodbye.
That's a perfect way to put it. The coherence is just completely diluted. The ordered input coherence is gone, paid for by a massive increase in thermal entropy.
The nuclear temperature.
The nuclear temperature, right. So the particles that fly out have a statistical energy spectrum. It's Maxwellian, governed by that temperature, not by the specific energy of the thing that came in.
But the sources mention a possible exception to this, a falsifier.
Yes, and this is where things get interesting. For lighter nuclei or near certain energy thresholds, the forgetting might not be perfect.
Coherence might survive for a bit.
It might. If a sort of intermediate, more coherent doorway state lives long enough, you might see little bumps in the spectrum that are not Maxwellian.
Echoes of the entrance channel.
Exactly.
Yeah.
High-resolution experiments are always hunting for those little fingerprints of memory.
So we've gone from the atom to the nucleus. Now let's go somewhere even more fundamental. The vacuum itself.
The background chaos.
As the source material says, the vacuum isn't empty, it's a tuning fork.
And this brings us to QED, quantum electrodynamics, and the Lamb shift.
The tiny energy split in hydrogen that wasn't supposed to be there.
It showed that the vacuum is active. The electron is constantly interacting with this sea of virtual particles, and that interaction actually retunes its own energy levels.
But the calculations for this were a nightmare. They kept giving infinite answers.
A total disaster.
Mm-hmm.
But Weisskopf was central to figuring out renormalization. The idea that you can sort of systematically subtract these infinities to get finite testable predictions.
So how does our coherence ledger explain this? What is the vacuum doing?
The vacuum is just background motion. The key is that we only care about the difference in how the two hydrogen states, the S and P states, interact with that background.
We don't care about the infinite total energy.
Just the coherence shifts. We use something called a coherence cutoff. Basically, we say that background modes that are too fast or too chaotic stop mattering. They decohere before they can affect the electron's phase.
So renormalization is really coherence renormalization.
In this view, yes. You're just carefully accounting for which background motions can still talk to your system coherently.
This idea of normalizing the leak is so powerful.
Yeah.
And it led to a really practical tool he developed, the Weisskopf unit.
Oh, yes, the Weisskopf unit. It's often just a footnote in textbooks, but it's incredibly useful.
What is it exactly?
It's a baseline. It's an estimate for how fast a nuclear transition should be if it were super simple.
Like if just one single proton jumped from one orbit to another.
The simplest possible picture. A stupid nucleus model.
And why is that so powerful?
Because real nuclei are never that simple. If you measure a transition and it's, say, 100 times faster than one Weisskopf unit,
It tells you something isn't simple.
it tells you the motion is collective, many particles are moving together in phase, singing in chorus.
And if it's much slower?
The motion is hindered, the simple path is blocked for some reason. It's a yardstick for how loudly the nucleus can sing, and it reveals all this rich, complex structure.
This is a perfect lead-in to his sort of grand unified theory of all this for scattering.
The optical model.
Right, which uses a complex potential, U equals V minus IW.
The real part V is what you'd expect. It's a potential that bends the path of an incoming particle. But the imaginary part, the W, that's pure Weisskopf.
It's the leak.
It's the mathematical description of the leak. It's the absorption. It quantifies how much of the incoming wave's coherence gets drained out of the simple elastic path.
And gets scrambled into the compound nucleus.
Exactly. It's the price tag.
The price tag on keeping your phase.
A bigger W means a higher price. It means the coherence gets converted to thermal entropy very, very quickly.
So it all comes together. He took all these chaotic processes and found the underlying arithmetic. He normalized the leak.
It's incredible.
And it leaves us with these two amazing insights. The first one is, a line is a life with a deadline.
Perfect.
And the second, which I think is even deeper, is, if you want to know how long a pattern lives, don't ask what it is. Ask what it can talk to.
It's all about connectivity. That's the grammar he gave us. If you can count the exit routes and price the leaks, you can connect everything from an atom's glow to the vacuum's hum.
So that brings us to a final provocative thought. Let's take this idea of a tunable vacuum and bring it to a totally modern context.
Like a cavity QED experiment.
Exactly. You have a superconducting qubit, your artificial atom, inside a high-tech tunable resonator.
So we're testing the Lamb shift, but in this incredibly controlled environment.
Right. Now, the standard view says the energy shift of the qubit depends on the vacuum's mode amplitude.
But what if our coherence cutoff idea is really fundamental? The question then becomes, what if you could engineer the phase of the vacuum?
Squeeze the vacuum states, or bias the boundary conditions in the resonator?
Then the prediction is that the Lamb shift, the energy level shift you measure, shouldn't just depend on the energy in the vacuum.
It should depend on the phase as well.
The boundary phase. It would mean the vacuum's effect is profoundly context-dependent.
Which would be a stunning confirmation. It means the vacuum isn't some universal static background. It's a medium whose properties are shaped by the local quantum geometry.
It just shows you how powerful this framework is. When you start tracking the flow of coherence, you see these deep connections everywhere. That's the Weisskopf vision.
Thank you for joining us for this deep dive.